request Naveen to carry on with his presentation. This one, I'll do something on.
I'll stop sharing the screen. Oh, I haven't stopped it. Yes. Yeah, basically I'll talk about two things. One is about adding the auxiliary variables to the pencil code, and second one is like we know that the pencil code solves all these MSD equations like hydro, magnetic field, and everything, and it will store all the data in the F array. So let's say if you're interested in computing certain diagnostic quantities, okay, there are already a lot of diagnostic quantities that are there in the pencil code, and if you see the manual, a printout in file, the appendix part, you can see that there are a number of variables that are given. Okay, let's say suppose for some application you require certain quantities which are not there, then how to include them in the pencil code. So these two things I'm going to talk about. First thing is like how to add the auxiliary variables. This is just simple, and this has been talked over many times by many speakers in this meeting. The first thing that you do is you go to the start.in file, which Samruddhi also talked about. Then there is something called hydro initial parameters. Okay. So for example, let's say in the pencil code, let's say let's focus on just two equations. There is like Navier-Stokes equation and then the vector potential equation. So when these two equations are solved, there are three velocity fields, three vector potentials which are stored in the F array. Okay. Now, if you want to calculate the vorticity, let's say, which is not default calculated, it will do the calculation wherever it is needed, but it will not store in the F array. Let's say if you want to store in the F array, the auxiliary variables in pencil code are called the derived quantities. Derived quantities of the fundamental variables that are there in the pencil code, like velocity field, vector potential, or density, or whatever. Okay. So for that, what you do is there are you need to look at the specific switches. So for example, LOO underscore as underscore auxiliary, if you put equal to true, then that particular the vorticity is stored in the F array. So before that, we need to allot this space in the F array. For that to do, we need to make a modification in the cparam.local. In the cparam.local, we need to increase this M auxiliary contribution to 9, because here I've used three auxiliary variables. Okay, I have to increase so many number of space in the F array. I hope your people can see this. Okay, M auxiliary contribution 9. So there is this Perl script, in the pencil code, which is written, which is a text manipulator or editor, language processor. So it will go and read all those files. Okay, it will read all the executable files. It will read all the input files, and it is written in such a fashion that it picks up this number and then inputs in the program and then allots the F array. So okay, then if you want to, generally by default the auxiliary variables are not written in the war files. If you want to write the auxiliary variables in the war file, then you need to set this something called lwrite underscore ax equal to true in the start.in file again. So then the auxiliary variables are written in the war.file. Otherwise, it will make a space in the F array. It will be utilized inside the pencil code, but it will never be written in the war file if you don't set this lwrite underscore war auxiliary equal to true. So let's just look at the files. Okay, like if you want to add a new variable, let's say, okay, new auxiliary variables, how to do that? So for example, if I'm interested in, let's go into this hydro.f90. Okay, the auxiliary variables. Okay, I'll come to this. Okay. So there is this program called register hydro. Okay. So let's say you want to include a new auxiliary variable which was not there in the pencil code. For example, we have added recently for our case for the correlation time measurement. Okay, something called the time integral value of the velocity field, which is called UUT. So what it does is that integral of U of t times dt. So every time step it will it will do the integration, and that particular value of the integral we are storing as an auxiliary variable in the FRA. So to do that, we define a new switch called LUUT underscore AX. Okay. Only when this is true, this particular what this register report auxiliary will do is, it will okay, this is the indexing, like okay, so we need to understand the FRA structure a little bit. So it's like a 4-dimensional array, and there are this first 3 dimension, the XYZ values of the variables are stored, and in the 4th dimension you have like 3 velocity fields and 3 vector potentials which are default. Okay, then if you add extra auxiliary variable, then on top of these 6 variables another 3 or 6 variables are added in the 4th dimension column. So in this IUUT is the index of that 4th dimensional column. Okay, and then because it's a vector quantity, so it has 3 indices, right? So all those indices we just have to give a name: IUXT, IUYT, IUZT, and this will accordingly assign the integer values to it. Let's say, for example, if you have 3 velocity fields and 3 vector potentials, after that, let's say if this is the only one auxiliary variable you're using, then IUUT will be 7. Okay, and then IUXT will be 7, IUYT will be 8, IUZT will be 9, something like that. So depending on number of auxiliary variables you will activate, accordingly the program will allot the integer value consistently without making an overlap. So this is the like subroutine which will do that indexing properly. So before like calling an auxiliary variable, we have to like register it in the FRA. Then once we do this registry, then we can just go ahead and do the computation where exactly that is used. Like this is IUUT, right? If you go here, so this is used in the module called time integrals hydro. Okay. Inside that, we are calculating the IUUT, like the integral of the velocity field. So each time step, the velocity fields are like multiplied to the time and then added to the FRA. Okay. And then, okay, once this is done, this information is there in the FRA, then it could be used for any other calculations or outputting the file. Okay. So now if we, okay, once we have used this switch, so there are a couple of places we need to make changes. Okay, so first I need to define it in the hydro dot like declaration variable. Okay, because it's a switch, and then I give a default value false. False, I don't want it to be always on, so I give a default value false. So only when I give it true that okay, I'll show you the next. There is something called the name list here, okay, which is called hydro initial parameters. So here also you can see that LUT underscore auxiliary is written here. Okay, so what it does is initially when the program runs, so it will take the default value as false, and then when this name list occurs, so it will go and read that run.in file. In that run.in file, if you have this LUT as true, then it will take that value as true. Okay, and then it will come down and then it will do the execution of the rest of the program. So you have like 2 name lists here. One is for the initial parameters, another one is for the run parameters. So this is the way like we include the auxiliary variables in the pencil code. And there is also one more thing, that if you look at this top header file, okay, there are like pencils provided, right? So what this program does is, let's say you want to add new pencils, you can just declare here. Okay, if you just write it here, again the Perl routine will go and read all these files, and whatever name it is there, it will create an according pencil in the cparam.inc file after it is compiled. That file I'll show you. And that pencil, for example, you can use it in pencil routine, for example, all pencils.
Viscous.
What is it called?
This is viscosity.
No, this is hydro module.
Hydro. Calculate pencils hydro.
Here you can go ahead and okay. And once you have defined new pencils there, for example, UU pencil. Okay, UU pencil is defined as the FRA. This is like x dimensional values are stored in this one dimensional value, and then at particular m comma n location, particular y comma z, and then it will be fed in that mn loop where it will be run across all the values of mn. And then you just give the indexing and it will store. So if you define a new pencil, for example, if you let's say curl, let's look at the curl. Where is it defined? Here, for example. Yeah, here. So here, if IO is not equal to 0, means if it is defined as an auxiliary variable, then those auxiliary variables like storage will be used in the pencils. If not, then there is something called curl _mn, which will be used to compute this p percentage O. Okay, this is something called the pencil type case. We'll see that. Okay, Samruddhi explained about this cparam.local and makefile.local. Generally, there is additional files which are created when you do the compilation. So let's look at that. Let's say I'm in the sample file. It will not be there in the actual pencil code directory because nothing is compiled in that. If you go to a particular sample directly where it is compiled, if I let's say show like cparam, okay, you can see here below. So cparam.local, which was already where we store the grid values and all. And there are two more files which are created: cparam.inc and cparam_pencil.inc. This is created by program itself. We don't create it. So here you can, if you go, if you store the auxiliary variables, all this, it will be created. Like for example, in the cparam.local, when I said the m auxiliary variable is 9, so it will go read that and put it in this place. And this cparam.inc is called inside other routines also. For example, if we look at certain hydro product 90, probably. Okay, it is included in the cparam itself. There is something called cparam.f90. Here it is. There are two files which are included, like cparam.inc and cparam_pencil.inc. Okay. This was not there before compilation. Only after compilation, these two files are produced. So this is an important thing to know. Let's just look at the cparam pencil also once. Okay. See, for this particular case, so there are something like 252 pencils are created. Okay, this is called the type pencil. This is a class variable, and inside that you have like different arrays. So this is a one-dimensional array. This is a one-dimensional array with 3 components. Like that, there are like 256 pencils that are calculated in the pencil code centrally, and it will be used to evolve the equations. So those informations are there in cparam_pencils.inc, which is produced by the Perl script. Okay, next I want to talk about now how to add the certain diagnostic tools which are not there in the pencil code. Okay, this is just a quick summary of the program flowchart, which you have already seen many times. It's like you have a hydro file. Okay, this Navier-Stokes equation is solved in this subroutine du_dt that is used in the equation.file, and in that equation.file, this is called inside RHS_CPU. Here many other routines are also called. Okay, we will also see that once. And then this this is the right hand side of the equation, which is called again in the subroutine PD. And that PD routine is called in the time step. Here we use the Rangekutta method or whatever other methods, like other derived methods of Rangekutta, we'll use it to evolve the equation from one time step to the other time step. Then this particular time step is used in run.f90 file, okay, where it will go through the main loop of the time. So this Hydro F90, it uses this global data file like cdata.f90 and this cparam.f90. And it also uses two other files which is produced by the pencil like Perl routine. Okay, let's just look at the equation.f90 once, just to show you what I was saying. So for example, if you look at the equation.f90, ut_dt. Okay, here you can see that this particular subroutine calculates the Navier-Stokes equation evolution. Okay, and then this DAAT_dt calculates the magnetic field, and there are like other subroutines for the other equations. And there are these switches, okay, called L magnetic, L Lorentz gauge, and all these things. You don't have to worry, because the moment you set the magnetic equal to magnetic in the make file.local, these switches are turned on true automatically by the code itself. So for example, if you go inside, I think here
it's made for
not cparam.ing. Yeah, let's see L magnetic. Yeah, here L magnetic. So the moment you turn on the L magnetic equal to magnetic in the makefile.local, so this program just reads those files and turns on the switches automatically. But there are like other switches, how to add them. So that's what I'm going to talk about. Exit. Okay, so this is a couple of examples that I picked up from my research. Okay, where I wanted to calculate the rotation measure of a magnetic field. So this quantity was not there in the pencil code actually. So I had made an implementation of this. I'll just show you how it was done. And then I'll show you one more example, like calculating the integral scale of the turbulence and the magnetic field. Okay. So for this, rotation measure, like you generally know that it is the line integral of the magnetic field along the line of sight, right? So which is rho times B dot dl. And then we define rotation measure for all three directions, because if there is an anisotropy in the magnetic field, then all three rotation measures will be different. Okay. So now, if you look at this rotation measure, if you integrate along the x direction, the magnetic field, then it will be a function of two variables, which is y and z. Let's say for this function. Okay. But since the magnetic fields are fluctuating and there will be positive and negative value, the average, if you take it, it will be 0. So we are interested in the sigma RMS value of the rotation measure. Basically, it will give us how this integral scales of the magnetic field, like at what scales the magnetic fields are growing. What is the dominant scale of the magnetic field in the simulation? That is the information is given by this RMS values of the rotation measure. So generally, RMS values of the rotation measure is we define as follows: like once we integrate over the x-axis, okay, this RMX is a function of y and z, and then we take the square of those values here. Okay, square of the values of the RM, and then average it over all the other two directions, which is called like okay, here, sorry, there was a mistake. Here it should have been square. Okay. So now the question is like how to implement this in the pencil code. As you can see that this is a box average quantity. Okay. So for the box average quantity, the way to go is like, let me just get into the routine. there is something called the printout in file. Let's say this is the one. Then, yeah. So we have. So first we need to decide for the name. What is the name that we're going to give for this particular quantity? The sigma RMS values in the XYZ direction. So for here, I have chosen SI RMX in the X direction, sigma RMY in the Y direction, then sigma RMZ in the Z direction. Yeah. So now how to implement this in the pencil code? Like if I want to calculate this. So I get into the magnetic field.f90. Yeah. So first is to declare a integer tag for it. So I'll tell you why we have to define the integer tag later. Like there are 3 sigma RM in 3 directions. So I define the 3 sigma each direction, like MX, MY, and MZ. Okay, here there are like 3. Then okay, let's see the routine. And then this is the program, subroutine, which actually calculates the sigma RMS that RM value. So here I have defined a new. This is not actually a switch. This is just a logical variable. Okay, if any one of this is non-zero, then you just activate this routine. Okay, this is implemented saying like this times R, this times R, this times R. Okay, then there is this routine called mean sigma RM. I'll just briefly go through this. Okay. So what we are doing is basically rho times the magnetic field. Okay. We are creating a 3-dimensional array. Okay, and then multiplying rho times the magnetic field in all locations. So this is a 3-dimensional array. Then what I need to do is next, I need to sum over the X direction first to calculate the RM, right? So now when I have to sum it over the X direction, for example here, I take this RBX, which contains the rho times the magnetic field. So in Fortran, we have something called sum. If I say just sum without this dim, for example, like this. If I just say this, okay, then it will just sum in all 3 directions. But if I just say like dim equal to 1, then it will just do the summing in one particular direction. Okay. Now when I do this sum, it will just do the sum on a particular current processor. Okay. So the value of the array, like each of the processor will have some array length, okay, pencil length, which is like a length nx, but the actual array is nx times the nc proc x, like the number of processors that are given in that x direction. Okay. Then I need to sum over all the processors which are there in the x direction. But generally, we use the MPI reduced sum for it. Most of you know that MPI reduced sum, we can use it for 2 purposes. One is like we can sum it over all processor, and then it can be stored on the root processor. That is one function of it. Then the other function is like I can broadcast it to all the other processor also. But here the function here it is slightly, I need it for a slightly different purpose. That is, I need to sum it only along the X-beam processors, not over all the processors. Okay. So in the pencil code, they have written, so there is something called MPI comp split function. They can use that to create a group of processors. Okay. Only for those group of processors, you can like do the operations. So in the pencil code, it is already done. So this is the IDR tag for it. For example, if you say IDR equal to 1, it will do just sum along the processors in the X direction. If you just say IDR equal to 2, then it will do the sum along the Y direction. If it is 3, then along the Z direction. And there are other 3, like also, it will also do the planar averages also, like planar averages of the processors. If you say IDR equal to 1, 2, it will do XY, 2, 3, then it will do YZ. Okay. So next thing is have summed over individual processor in the x direction, then I use this MPI reduce with this tag to submit along full direction of the x. Then this value is stored only on the processor where IPX equal to 0. IPX is the tag of a processor. Okay, there is something called these are the global variables IPX, IPY, and IPZ. Okay, so now since this is done, the sum is done in the x direction, so it will be stored on the IPX equal to 0 processor only. Okay, so the next thing I have to do is square this quantity. So now in the temp, the scalar is sitting. Sorry, the two-dimensional array is sitting. I pass it to MPI reduce, and then it will sum over all the processor and put the value in the RBX temp. And then I need to like square this, okay, with certain scale factors I have used. Then once I have squared this, again I have to sum it over all the other like YZ processors. That is how I have done it. Okay.
So why is it 23?
23 is summing over YZ. So this is a special group of processors that is created in the pencil code. Mostly I have seen that nobody uses this. So only IDR1, IDR2 they have used it. Only for the what is it?
Okay, this is an option and you can choose the number of processors. So that's why it is 23 so that people don't confuse it with 1, 2. And 3.
No, it is not number of processors. It is the direction. It's like you have processor layout in XYZ, let's say. Okay. So for example, let's say look at the sum. Okay. You have three-dimensional array. When you say dim equal to 1, it will do only sum in the first direction. Then it becomes a two-dimensional array, right? But that will only happen on the individual processors. Let's say you want to sum it across all processors, right? Like there are like array like this. You want to sum it only in the x direction, but you don't want to sum in the other two directions, right? If you just use normal MPI reduce sum, then it will just sum up all along across everything.
And give a scalar.
Yeah, give us a scalar. Okay, but here I need to just sum it along the x direction processors only. So there is MPI comp.f90 where they have to create this group of processors actually. It is not default, so it is created. So x direction processors are created, y direction processors are created, okay. Then the z direction, then planar processors are created.
No, so I did not understand what is the difference between saying I did 1 and then saying I did 2.
Okay. Okay, IDR1 it will do the sum along x direction. IDR2, 3 if I say, it will do the sum along YZ direction, both. Planar average it will
But
do.
not x.
Not x.
Okay.
So once we have done it along x, so the only direction that is remaining is YZ. Now I square this quantity. Okay. This this RBX temp, which is now contains all the like summed value across all the processor, like X processor. Then I use this here. Okay. I again replace it here. Rewrite the temp because I don't want to use the extra space. Then once I do the sum, all the like summed values in this. Now this is on the root processor. So then I write it in this value like sigma RMX. Okay, then there is a routine called, okay, this is one thing we need to understand about pencil code. There are this arrays called fname array, fname xy, fname z. So fname generally stores all the volume average of the quantities. So URMS, BRMS, okay. And then if you want to store the, let's say the xy averages of the quantity, then it will be stored in fname z arrays. Okay. So if you go on,
it's only a function of set.
Yeah, but now it's a volume average quantity, just a number for each time. So if we I could show that, but let's me skip it. It will become too much. So once what it does is it. I'm here, right? Save name. So it is stored in that fname array. Okay, once it is stored in the fname array, I have to now output and write it in the time series data. So for that, there are already like built-in Yeah. So this is one more program called rprint magnetic, which is called in the start.in file, start.f95. Okay. So what it does is, once I declare a new variable, I need to new diagnostic variable, then I have to write it here. Okay, here. Okay. So this is something called parse name, which is a routine. What it does is, before running the code, okay, it is called inside the start.f90 file. So what it does is, it will go read all your print.in file, okay, and stores all of those values of the print.in, whatever you have given, like urms, brms, in the cname array, which is a character array. And then it tries to match us with any of this label here that you have given. If it matches, then that particular integer variable is given certain integer value. That idea, for example, in our case, here, okay. So it will match this to, if it is there in the print.x, this name is there, then this particular idea sim, is given certain integer value depending upon at what line it occurs. Okay, once it is there, so in the run.in file, when this program runs, it uses that value and that particular module is switched on. So we can just go and look it up here. For example, the print.file. Okay, here in the print.in file, like I have said, like sigma rmx, sigma rmy. Okay. So then it will be written in the time series dot file. So if you look at the time series dot file, so here we can see this entries. So here it is written. Okay. So one can use any plotting modules like ideal or Python. Maybe I have some plots here. Maybe not.
I can time series plot.
Wait, I can do the plot RM. Maybe it will do the plotting. No, I have to source it. But I remember having it. Okay, let me just open the file and see what is there. This is not the one. Yeah, this is the one. So here I have stored it. It must be there. If it is not there, let's just run it. Okay. I'll just source this. Okay, now it is sourced. Which folder I was in?
This was Dynamo non-hell 512.
Okay. So now if I run that, should run it. So this is the Python routine file, which is used to plot, read the time series data. So there, like, says so many lines are read. And this is the sigma RMS value in all three different directions, X, Y, Z. But this is isotropic run, so all three directions are same here. So there is no preference. So if you put in any anisotropy like shear or any differential rotation, then the directions, like the sigma RM, will change according to the direction. Then I have a last case where, yeah, that's what. Then declare it in the rprint.magnetic, then it will read it. Okay. For this particular case, you did not require any particular switch because this was a volume average quantity. We could do this in the print.in file. Let's say you want to calculate certain other quantities which are, you want to output your own file. That is the case. Okay, here I'm trying to calculate the integral scale of the turbulence and also the magnetic field. So integral scales are generally defined as the integral over the correlation function. So this is the correlation function of the velocity field, which is taken at the point x plus r, then at x, okay, at the same time. So I can define the three integral scales for the three different directions. So this, if it is like an homogeneous, if this is like, if the turbulence is homogeneous, then this will be like a function of just r. Then if I integrate it along the rx direction, then I will get the scale of the turbulence in that particular rx direction, right? And then I can define other two scales also like that. Similarly, it will basically tell me what is the dominant scale of the turbulence, like where the energy is maximum. So I am doing this in the Fourier routine because doing it in the real space is a bit tough because of this convolution. So in the integral space, in the Fourier routine, it becomes just a product of the velocity field, right? So then in the integral scale, this is the expressions of the integral scales in the, if I write it using the power spectrum. Okay, so here it is just the average of the power spectrum over all scales. For Lx, I need to put kx equal to 0 and then sum over all the other two directions, y and z. Okay, so now let's see how this is like to be implemented. Okay, first to do that, okay, we need to like add switch to this. So for example, we need to make a change in the power spectrum.f90. Okay, we need to add a subroutine. Once we add the subroutine, then we need to make that public so that it becomes available to all the other programs. So then I need to declare the program in the power spectrum.h. Okay, then I need to introduce a switch for this particular subroutine. Okay, because I need a freedom whether to use this routine or not. So once I add that switch, like previously that I showed. So in this case particularly, I need to add here in the param_.io. Okay. And then once I add the switch in this, then I need to declare the default value of the switch in the global file c.f90. Here I generally say that the switch value is false. And then once I include the switch in the run.in file, then that will be turned true. So let's see how it is done. So let's say power spectrum.f90. Okay, here I am calculating the integral scale of the turbulence. Okay, so this is the FRA, and then SP is just a name tag. I can use it for a velocity field or magnetic field or the vorticity field. Okay, so I collect the value of the velocity field in this ERA, and then I do the Fourier transform using this FFT XYZ parallel, which does it in a parallel fashion. Okay, so as I'm like, I give the real values of the velocity field here. Then after it does the Fourier transform, it will give me the imaginary and the real part here. Okay, then I do the square of this, and then I again use that like sum across, because in the first, if you remember, if you see, I need to do just, okay, sorry. For example, if you look at this equation, I need to just do the sum along YZ direction, that's it. The kx lies on the first indices itself. So the first integral I do along YZ, the second integral I am doing the sum across other two directions like x and z, the same way for the others. Okay, once I write this subroutine, for example, here integral underscore dot scale. Okay, once I write this, then there is something called the header file, power spectrum. This is an old practice for the Fortran. Okay, normally in the new practice, I mean generally this information will be there in the F90 file itself in the module block, but this is just an old practice to have this header file. So once you write here, it becomes publicly available to all the other routines wherever we are using. Okay, so we need to declare here in the power spectrum.h. Once we do that, then this power spectrum file is actually called in the snapshot file. But here I introduce actually the switch. This is how we introduce the switch. Okay, L int underscore scale. So when this is turned on, only then the the integral scales are calculated. If not, it will not calculate. So it is called in the snapshot.f90. This snapshot.f90 is again called in the run.f90. Okay. So once I introduce it in snapshot f90, then I need to declare it in the global variable, global file like c.f90, which is this. Let's see. Okay. So now I write the default value as false here. Okay. In the c.file. Only when I say it in the run.in file, it will be read, and then this particular lint underscore scale will be made true, and only then the module will be turned on. For example, here in run.in, I am saying here in the run parameter itself. Okay. In the other cases where I had mentioned that we have to say it in the hydro run parameters because it was not written in the param underscore.io. Okay, that switch was just local to that particular file. This kind of a global switch, which all the other routines can see. So that's why we have to say in the the top part of the program. So this is the way we add these switches in the pencil code. Like when you want to add certain subroutines, then if you want to add the switches, then you say it in the these are the two important files like param dot. So these are the two places you need to declare it, and then the corresponding header file. Here I have used power spectrum.f90, then I have declared the routine here. If you make changes in the other files, then you need to declare in the corresponding header files. Okay, so this is how it calculates. So the power spectrum, I have a routine written. That routine will be called in the snapshot f90. That particular routine is power snap. Then it will be fed in the that is already there. Okay, so in run.f95. Yeah, I'll stop here.
Thank you, Naveen, for showing us how to add new diagnostic variables and averages and power spectrum. So these are checked in, right? That's a light there.
May I ask here?
Yeah, Matthias, go ahead.
Do you hear me?
Yeah, please go ahead, Matthias.
Yeah. So I have not seen that very properly. So I have the feeling that you both that you calculate the integral scale both for the velocity and magnetic field. Is that true?
Yes, yes.
Okay. Could you show that piece of code where the calls are?
Yeah. I'm sorry. Yeah, here it is.
Yeah.
So here, yeah, I just take the FRA. Okay, for
No,
example,
I mean where it's called. I think it's inside snapshot then.
inside snapshot.
Where the switch is asked for, and then the call is done. I think it was here, right?
Yeah, here.
Exactly, yeah. So and the first is the first is for velocity, the second is for magnetic field. Yeah, it would be very desirable to, in order to avoid trouble, to ask also whether magnetic is active and hydro is active. Hydro in the sense is perhaps always active, but magnetic at least is not always active. So you should
maybe
ask.
I should just write here that L magnetic.
Yeah, and yeah.
Yeah.
Otherwise, it will perhaps crash, and that's not needed, because it may happen, as Axel pointed out, that you change your setup a bit and forget about removing these switches, and but you have removed magnetic from the setup, and all of a sudden it crashes.
But if you look at this magnetic spectrum, for example, here,
yeah,
this you don't see L magnetic switches.
Yeah, but we have discussed that, and we can do that specifically in order, or in the way that the no magnetic module simply resets the switches. If the
suited
switch is specific, like mark spec is a specific switch for the magnetic field, then this switch will be reset if there's no magnetic instead of magnetic included. So no trouble. But your L-int scale is not specific. And that's why you have to ask here for whether the module is present or not at this place. It cannot be reset somewhere else. So about hydro, I'm not quite sure, because no hydro is also doing something, but I'm not sure whether it's really defining a proper U array. So it might be also in order to put here an L hydro and L in scale, but that's, I had to look it up what no hydro is really doing. But in magnetic case, it's completely clear that no magnetic is not providing any magnetic field.
Yeah.
That's why we have to ask here.
Okay, yeah, thanks, Matthias.